Is it working? Okay. Thanks for the introduction. Thanks for the organizers for inviting me and bringing on this nice workshop. It's been really fun so far. So I'm going to be talking about some work I've done with John Selby. So we're both at the Perimeter Institute. It's going to be based on these two papers, and it's called GPT-Safe Cryptography. Okay. So it has cryptography in the title, but don't worry too much if usually this is quite, not everyone likes cryptography. Okay. But it's really about convex optimization mostly. Okay. So let me give you a quick abstract to see if you want to continue paying attention. Maybe you want to work on your own talk or whatever. I'm going to be talking about GPTs. Okay, these are generalized probabilistic theories. Okay, so this is what happens if you take quantum theory and you want it to be more convex. Okay, so it's going to be some kind of physical theory. Everything is still going to be linear. Okay, so linear down here, but we're going to keep the convexity. Okay, so that's just very quick. And I'm also going to be talking about cone programming. Okay, this is going to be the main tool that we use. Okay, and this is basically optimizing linear functions over convex sets. Okay, so if I go back and forth many times, you'll see there's lots of words in common. Okay, so cone programming is going to be perfect for studying GPTs, and this is basically the abstract. We're going to optimize GPT stuff. Okay, so everyone here is probably very familiar with semi-definite programming, and we've been convinced that this is very useful for quantum information, quantum computation. And basically, you can just lift the analogy from semi-definite programming to cone programming. In the same way, we're going to lift quantum theory to GPTs. Okay? Okay, so let me start with a cone program. So it's just a convex program written in a particular way. So we're going to optimize some kind of linear function. Okay? And there's some kind of nice affine constraints. But now x is going to belong to some generic convex cone. Okay? So we've seen linear programming and semi-definite programming. This is just special cases whenever k is equal to the set of non-negative vectors for the case of linear programming. Or if this is the set of positive semi-definite matrices, then you get semi-definite programming. Okay, so this is a bit more of an abstract thing. And this is completely general. Any convex program can be written like this. Okay, for a particular nice choice of affine constraints and a nice choice of cone. Here's the geometry. Okay, so you have some kind of nice convex cone here, and you have some kind of affine slice of it. Okay, just like it's probably the picture you'd have in mind when you look at semi-definite programming. Okay, so you just want to look at x that belong in the intersection here. This is still the feasible region. Okay, so that's very quick cone programming. What is a GPT? Well, a GPT. I'm basically going to describe quantum theory, except I'm going to use general convex cones, okay, instead of the set of positive semi-definite matrices. So physical states belong to some cone K, okay? We'll normalize them in a second, but that's physical states belong in some cone. The set of measurements belong in a different cone, okay? We call them effects, and it's some other cone, okay? And now we're going to use a particular effect, the throwaway effect or the discarding effect, to define the set of physical states. Okay? So there's some kind of view here that belongs in this cone, and we're going to use it to define this hyperplane. All things in this cone K that make inner product exactly 1 is going to be the set of physical states. Okay? This discarding effect, you could think of as being the identity or tracing out a quantum system or the partial trace in quantum theory. Okay, so if this is the set of positive semi-definite matrices, this E here, or sorry, this U would be the identity. Okay, so we have states and we have a particular discarding effect. We know how to throw states away, but we can also define a measurement. So just like in quantum theory, the inner product is going to correspond to some probability. Okay, I'll explain that in a few seconds. And probabilities, we want them to be non-negative. Okay? So there's a way to talk about if you take vectors in cones and we want them to be non-negative, and that's the dual cone. So if you have a cone K, K star is the dual cone, and it's going to be all vectors that make non-negative inner product with everything in the cone. Okay? So that's a dual. And we require that the effect cone is contained in the state cone's dual, like this. Doesn't have to be equal, but it's going to be contained. Okay? And this is going to enforce that the inner products are all non-negative. Okay? And there's a symmetry here. If the effects are contained in the dual of the state cone, then the state cone is contained in the dual of the effect cone. Okay? Because duals work nice that way. So we have non-negative inner products. Okay? If we have a measurement, it's going to be a collection of things in this cone, such that when you add them up, you get the discarding effect. Okay? This is just like in quantum theory. If you have a bunch of positive semi-definite operators that add to the identity, you have a valid measurement. Okay? And we define everything like that, such that the probability, if you have the state K and you measure with the effect EI, the inner product is going to be the probability of that outcome. Okay? And everything I've defined so far makes the probabilities non-negative and add to 1. Okay? So this is basically GPT. If I asked you to take quantum theory and just say, okay, replace all the cones with generic cones, after a few minutes, this is probably what you would come up with. Okay? It's quite natural. Okay, so cone programs and GPTs play very nice together. We just basically have a bunch of these affine slices, a bunch of convex cones, linear functions. So everything's going to play out very nicely. Okay. Are there any questions at this point? This is a very short talk, so feel free to ask as many as you want. So the states belong in some cone, and yeah. So you specify the state cone, the effect cone, and then there's some special thing that belongs to the effect cone, and you use it to define everything, basically. Yeah, pretty much. There's a lot more things that you need in a physical theory that you need to define a way to compose systems and some other physical principles, but this is like the extreme bare bones version of GPTs. So Howard's going to talk about GPTs on Friday mornings, so we'll have a whole hour of fun. This is like the 5-minute version. Mm-hmm. Oh, okay. Okay, great. When's your talk? When do you speak? Tomorrow. Okay, perfect. I should also say I've generalized quantum theory. Basically, I shouldn't say generalized because these cones could just be non-negative vectors, which gives you classical theory. But I'm basically throwing away everything else you know about quantum theory. Like I'm not assuming there's entanglement, purifications, tomography. Really, I'm just saying you have two cones, and they play nicely together. Okay? Any other questions? Is it okay? Okay, so these guys play nicely together. So we have a setting, which is GPTs. We have a tool, which is cone programming. Now we need some kind of problem to solve. Okay? And we're going to look at two cryptography problems. Okay, so this is where the cryptography comes in. So a bit of a sales pitch, why we care about this. So we have very good quantum cryptography. Okay, and this is very nice. But whenever you study quantum cryptography, all of the security proofs assume the validity of quantum mechanics as a faithful description of nature. Okay? If one day, or 100 years from now or whatever, someone comes along and says, hey, look, quantum theory isn't the ultimate description of nature. We have this new theory. Okay? Quantum mechanics doesn't do everything. It has a hard time explaining gravity, black holes, all this good stuff. Okay? So there's no reason to think that down the road we're not going to have a new theory. If you assume the validity of quantum mechanics to prove the security of your protocol, okay, like BB84 or whatever you want, then you have to reassess everything. Okay? What's secure and what's not secure. Just like whenever Peter Shor came along and said, hey, now we can do discrete logarithms and factor, we basically had to reassess all of classical cryptography. Okay? So one reason to look at cryptography in the GPT setting is to kind of future-proof some of these security things. Okay? If down the road you say, hey, now I have this new theory, it explains quantum mechanics and Newtonian mechanics and everything, but also describes gravity now. If it has some certain physical principles that still hold, then results from your GPT proofs may still hold. And so it's kind of like future-proofing some analysis. Okay? And if that's a little too exotic for you, and you really like quantum, and you probably should, studying GPTs is a way to kind of look closer at quantum theory. Okay? If you have a proof that works in quantum, it's nice to see what parts of quantum make your proof work. Are you relying on superposition? Are you relying on entanglement, purifications, tomography? Whenever you have a quantum proof, you're not usually assuming all of these things. Okay? So it's kind of a nice just to see the bare bone structure of quantum theory that allows these things to work. Okay? So it also lets you, instead of future proofing, if you just want to have a closer look at quantum theory, this is another way to look at these proofs. Okay? So anyway, that's the sales pitch. Let's go back to the interesting convexity stuff. Bit commitment. Okay, so bit commitment is a story between Alice and Bob. So Alice has a present for Bob. The problem is that Alice is traveling during Bob's birthday. Okay? She doesn't want to give Bob the present before she goes because Bob will open it up before his birthday and that would be terrible. Okay? So what she's going to do, she's going to put the present into a safe, send the safe to Bob, and now unless Bob is very strong, he's not going to be able to get his present. Okay? So now, some time elapses. Now it's Bob's birthday. He's eager to get his present. So what does Alice do? She sends the key to Bob via mail, or maybe it's a digital combination. She just emails Bob. So he applies it to the safe, and alas, he gets his present. And he has his present now. And it's his birthday, so everything is good. Okay? So bit commitment, or physical bit commitment, is kind of an information way of implementing this safe box. Okay, so what's going to happen? So since this is bit commitment, Alice is going to have two things that she may wish to encode, 0 or 1. Okay? If she chooses 0 or 1, she's going to create some bipartite state. Okay? So it's a state that lives in two physical systems. Okay? You can think of it as being entangled if you want. We're not going to assume entanglement, okay? Because it's a GPT. In GPTs, you're basically not allowed to assume anything. Okay? And then after some time, so this is this is right now, and this you could think of as being Bob's birthday. She's going to reveal A, and the rest of the system script A. Okay, so before Bob just had some physical system that he was storing in his lab. Now he knows the value of A, and he gets some other physical system that he can also put in his lab. And he has some kind of two-outcome measurement, okay, accept or reject. So now Bob knows there's two states that may have appeared, and he now knows A as well. So now he can just decide whether he wants to accept or reject it. Okay? So if Alice was honest and created the state SA, and she didn't tamper with it at all, then Bob's measurement here should accept with some reasonable probability. Okay? I put 1 here because it's just easier for the slides, but as long as it's more than, say, randomly choosing to accept or not, that's totally fine. Okay? So this is some kind of cheat detection that's kind of baked in to see whether she cheated or not. Okay? And the goals of bit commitment, there's two opposing tasks. Bob should not be able to learn the bit early. Okay? Just like in the birthday example, he should not have gotten his present early. However, Alice should not be able to change her bit before revealing. Okay? After this message B is sent, this is supposed to commit the value of B to Alice. Okay? She should not be able to change it. In the birthday example, she should not have been able to change, say, the color of the car. Okay? The car in its true form was already committed to. And now we're going to look at how much they can cheat. Okay? So I should stop. Any questions about bit commitment? Is the task clear? Okay. So we're going to show that this is impossible. Either Alice or Bob can cheat. So let's look at how much Bob can cheat. So picture yourself as cheating Bob. He knows he has one of two states. He has the reduced state if she chose 0, and he has that with probability 1/2. And with the other probability, he has the reduced state for S1. Okay, so he has one of two states, physical states, given to him uniformly at random. What he can do is, this is called the state discrimination problem. He has to choose, he has to decide which one he's given. Okay? He doesn't have to worry about preserving the state. He can perform a destructive measurement, if that's what's in your theory. He can do whatever he wants, he just wants to learn the value of A. So we can write this down as a very nice cone program. Okay? So we have two effects that belong to the measurement cone E, okay? And they add to the identity. This is a complete algebraic description of everything Bob can physically do. Okay? This is the probability that the measurement he chooses is correct. Okay? So with 1/2 probability, he's given this state as 0. And conditional on given that state, this is the probability that he correctly guesses the state is 0. Okay? And over here, this is the outcome whenever the probability that he correctly guesses 1 had he been given 1. Okay? So this is a well-defined probability and a very nice cone program. Okay? Okay. I don't have the cool animation for magic, but we have the dual problem. Okay, I'm just appearing. So we want to minimize XU here. So U is the discarding effect, and X is just some vector right now. Okay? So X is going to be larger than 1/2 of S0 in this partial ordering induced by this cone E star. E star is the dual to the effect cone. Okay? And X is also larger than S1. So it's simultaneously larger than both of them with a scaling factor. And we want to minimize this quantity here. Okay? And assuming your cones have enough interior points, you can use strong duality. Okay? This also holds in cone programming. And you get that these two values are equal. Okay? So the nice thing is now we have another algebraic description, and this is an exact characterization of how much Bob can cheat. Okay? And this, the nice thing about duality theory is this has given us a completely new perspective. Like if I just wrote down this cone program over here, it looks nothing like the problem of bit commitment or trying to learn one of two states. Okay? It's a completely new perspective. And we're going to use this. Okay? This is almost useful. Okay? We're going to tweak it just a little bit. It'd be really nice to have K instead of E star. Okay? So remember, K is the set of physical states, and E star is something slightly larger. Okay? So we're going to assume that these two guys are the same. We're going to assume that the set of states is equal to E star. Okay? But this is okay, because other people do this too. Okay? And moreover, it has a name called the no restriction hypothesis. Okay? So in GPTs, this is an assumption. It's a physical principle. Okay? So you have some kind of generalized probabilistic theory, and we're going to assume the set of measurements and the set of states have this nice duality theory. Okay? Not every theory you can conceive will have this property, but a lot of nice ones do, such as quantum mechanics, classical theory, so on and so forth. Okay? Because the restriction is you're looking at the restriction of the states, and you're saying, hey, look, the states only live in this small cone. But if you don't restrict it, then you're allowed anything in the dual cone. Did I get that right, Howard? Sounds good. He's much more of an expert than I am. Yeah, so that's a no restriction hypothesis. So with that, we're going to change this E star over here to K. Okay? Now something really neat has happened. The dual, which was this algebraic thing, now actually has some physical meaning. Okay? This K here is a set of states, physical states. And now this X, being larger than S0 and S1, also belongs to this cone. Okay? If you're larger than something in the cone, then you have to be in the cone. Okay? So X is now in the cone. If you scale it down by the objective function here, XU, we get a physical state. Okay? Let me remind you of physical state. This thing, inner product with U equals 1, which is the definition of a physical state. Okay? This actually also showed up in Fernando's talk, where he just took X divided by trace of X. As long as you start with something positive semi-definite, you're going to get a density operator. Okay? So this is a physical state. And moreover, this XU, this inner product, the scaling factor, is exactly how much Bob can cheat. Okay? So we're kind of hard-coding Bob's cheating probability into some physical state. And this physical state has nice properties because it's larger than these reduced states. So, through the magic of duality theory, we now have some physical state. What can we do with it? Well, Alice is going to use it to cheat. Now we're going to see how much Alice can change her commitment from 0 to 1 or 1 to 0. So she's like, okay, well, that's nice. I solved Bob's dual. Now I have this physical state. I'm going to actually send it. And she's going to maintain a purification. Okay? So purification is yet another physical principle we're going to impose on our GPT. So we had no restriction hypothesis and purifications. Okay? These are things we take for granted in quantum theory. But in GPTs, you have to assume it and make it clear you're assuming it. Okay? And if you do that and she maintains purification, just a few lines of math, since the dual constraints, you get that she can cheat with probability at least 1/2 divided by this inner product. Okay? So, since she can cheat with this probability, and this inner product down here is how much Bob can cheat, you combine them, and it's very simple. One of them can cheat with probability 1 over square root 2, which is about 70%. Okay? Ideally, so this is no-go. Big commitment is a no-go, assuming these two things. Okay? Ideally, we would want them to both to be 50%. That's the probability of Bob having no information, just randomly guessing the bit, and the probability that Alice basically has no control. And she has to decide her bit at the very beginning and stick to it. Okay? So this is a constant gap between the ideal case and not, so no go. Okay, and I'll just advertise a similar result was also shown by Carabella and others. Okay, it was quite a bit longer. This proof is very short, but some big commitment is sometimes possible. Okay, so Howard and friends here, they showed that if you have non-classical theory but no entanglement, then you can still do big commitment perfectly. Okay. And this is not a contradiction because I was assuming purification. So purification allows you to have some sense of entanglement. Okay? So roughly thinking, entanglement is really kind of what allows for big commitment, or the impossibility of big commitment. Any questions about big commitment? It's okay? Some people have strong feelings about big commitments, so we have a bit of time if you want to share them. It's okay? Okay, so the second thing I want to talk about is unforgeable money. Okay, so this is how money looks. There we go. Okay, so we're going to assume the bank creates the money and verifies the money. So the bank creates some paper money. It's going to send it out into the wild, and there's lots of people out there who really like money, and they may wish to counterfeit it. Okay, so they put it into a counterfeiting machine. Now there's 2 copies. Send it back to the bank, and that's bad. Okay, we don't want people to counterfeit money. So is this possible? Is it possible to counterfeit money? Well, here's the idea. The no cloning theorem should make this impossible. If somehow you put some kind of physical states, think for a second, just think quantum states. If you put them inside the money, then it should be hard to copy it because you can't copy unknown quantum states. Okay? So no cloning makes this impossible. That's the idea. But in reality, you have to measure clonability. Okay? You can't just have some kind of physical state, send it away, and later receive two states that are like, yeah, these are not the same. Okay? You have to somehow infer the information that they're not the same. Okay? And you're going to do that by measuring. You need some kind of verification, some measurement on these states to check if they're the same or not. Okay? And we know we can't copy quantum states, but perhaps it's the case that you could always get around any kind of verification they do. They're not perfect copies, but it'll pass any verification that you try to do. Okay, so that could be possible. So let's set this up. I should also say this is like the very first application of quantum cryptography. Okay, Stephen Wiesner came up with this application back in the 1970s. Okay, and it was in a seminal paper that inspired BB84 and others. Okay, so this is basically the oldest quantum application. Okay, and this is his idea. So you have some ensemble of states, and you select one with probability pi, and you put it into the banknote. Okay, let's not worry about decoherence or anything. It's just going to stay there. Okay, so now it has something inside that people outside don't know. And so the banker knows the state. This guy doesn't know the state. So before we talk about him trying to cheat, let's talk about what his attempt would be. What is his goal if he wanted to cheat? So he's going to send the money back. I should say, if he were to send it back untampered, the bank has some kind of effect here that they'll apply, and they'll accept the bank note with probability 1. Okay? They'll look at the serial number, say, okay, this was the state that we selected from the ensemble. They apply this effect, and it's accepted with probability 1. Okay? So that's what he's going to do. Let's assume this guy tried to counterfeit. What he might do is create some kind of joint state. Okay? I don't know if the theory may or may not have entanglement, but maybe there's some kind of joint state that can get around two different measurements of accept or not. Okay? And you could assume he's clever. You send them back to two different banks. Bank 1 is going to measure and accept with this probability, and bank 2 will measure and accept with that probability. Okay? And it doesn't matter what kind of tensor product you put here. Okay? There's lots of choices of tensor product in GPTs, but this is just saying they're in two different locations. Okay? So that's what a counterfeiter is trying to do. Now let's assume that he can't counterfeit one ensemble. Here's the idea. Just put more ensembles in. If he has a hard time copying one, he should have a hard time copying many. Okay? That's the idea. And this is what happens in quantum theory. So if you have n copies, they can even be the same ensemble, and the person copying may know exactly what that ensemble is. But let's say you have n copies of it, then the probability of copying n is going to be the probability of copying one of them to the power n. Okay? It kind of seems obvious at first, but it takes a bit of proof to show this. Okay? Mm-hmm. Mm-hmm. Yes. So yeah, okay, so you can write it down as an STP. You take the dual, you do some magic, and then you get a perfect parallel repetition. Yes, yes, everything magically multiplies. Yes. So that magic proves that there's no kind of joint strategy. If for some reason if you give it n ensembles, you could think of doing some joint thing, but the best thing you do is just try to copy each one individually. Okay? And that magic just comes from duality theory, and it was just completely algebraic before. In this paper, we actually show a physical reason why this parallel repetition result comes about. And it's completely physical argument. Yes, yes. It doesn't hold for an arbitrary STP. Dmitry Pashishnik has this result in 1990-something. So there's a very large class where you have this perfect parallel repetition. This happens to be one of them. Yep. Yeah. So we get this. So as long as there's some kind of quantum ensemble that you can't copy, in fact, any of them basically, because of no cloning theorem, you can get very good security. This decreases exponentially in n. Okay, so take your favorite ensemble, you're done. In the GPT case, we can make this hold under certain assumptions, but assumptions are bad in GPTs. If you have a result in GPTs, it's nice to have as few assumptions as possible. Okay, think of it as future-proofing. Okay, so this is what we're able to show. As long as your GPT has one ensemble, any ensemble, that you cannot perfectly counterfeit. Okay, doesn't matter what it is. It doesn't matter if you can counterfeit the rest of them. You just need one. The existence of one ensemble, and then you can, if you have n copies, it'll decrease exponentially fast in n. Okay, this is not alpha 1 to the n, but it is something that decreases exponentially fast. Okay, and the trick is we just upper bound it by something, and then we upper bound it by something that does decrease exponentially fast. Okay, so there's a lot more work you have to put in the GPT case than the quantum case. Okay, looks like I have a bit of time, so I'll go through this proof. Any questions about this? Like what I mean by quantum money and basically, the only assumption I'm using here is the existence of an ensemble you can't perfectly counterfeit. And I'm assuming the cones are closed now, which is something most people assume. The first page of a convex analysis book, assume K is closed. Okay, so it's an okay assumption. Yeah. So you look at the joint state. You optimize over all joint states. Actually, I'll show you the cone program in a second. We optimize over all counterfeiting machines such that the success of cheating is strictly less than 1. Okay, and this is in the supremum. So in the limit, it's still strictly less than 1. So it'll probably be clearer after this slide. So this is what we're actually optimizing over. This is the convex program. So we want to look at all linear maps. Everything has to be linear still. So we have a super operator that's going to map K to K tensor K. You take 1 copy, you output 2 copies. And there's some physical principles these linear maps have to satisfy. No, please. Mm-hmm. Yes. Okay, yeah. So we're turning 1 node into 2 banknotes. It's just the amount of copies inside of each banknote is now n. So if any of them fail, they know that it was tampered with. Yeah, so they have to pass them all. So right here, basically, I want to capture generalized quantum channels to the GPT setting. And this starts getting a little bit interesting because, so now we have the space of what linear operators we need. We need it to be trace non-increasing. Okay? Usually we want trace preserving, but we're going to allow the extra generality of non-increasing. Okay? And this is physically relevant, possible because you may perform some kind of operation, perform your own measurement, realize that, that it's going to fail and just abort. Okay? So this is something physically possible. So trace non-increasing and a valid GPT channel. So this is where the cone constraint comes in. So if you had this as a valid quantum channel, you'd want this to be completely positive. Okay? Completely positive super operators are a nice, very nice convex cone. Okay? But completely positive is not exactly what we need in GPTs. We need the input to be states and the output to be a state, even if you only apply the channel to a subsystem. Okay? So this is completely positive, but for this, we need this to be completely cone preserving. Okay? It has to preserve the state cone. Okay? But something sneaky that comes in is that you could also look at the Heisenberg picture where you're evolving the measurements. So if your channel is evolving the measurements, in quantum you still want completely positive, but now we want completely effect cone preserving. So it has to preserve the cone when you're evolving the states, and it has to preserve the measurement cone when you're going backwards, when you evolve the measurements. Okay? So there's lots of neat things that get into this val GPT channel. Yeah, then they might be. Yeah. 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 But yeah, we're not assuming that right now. Yeah. So there's lots of convexity here. Now, if you had a quantum channel and you want to optimize over a quantum channel, usually what you would do is you apply the Choi-Yamakowski isomorphism, and now you have matrices that are pos-semi-definite, and now we have semi-definite programming, and everyone's happy. Okay? But you don't have to apply this isomorphism if you just want to stick in convex land. Just optimize over the set of channels. That's totally fine. That's a nice convex set. Okay? So that's what we're going to do. Basically, just stick to that. Oh, right, the objective function. So with probability pi, you're given this si. Okay? You're going to apply your counterfeiting machine phi. Now you have some joint state, and this is the probability that's going to pass the verification. Okay? So let's say if you want to pass a probability 1, for each SI, you have to perfectly pass this acceptance probability. So you have to perfectly counterfeit. Okay? So, cone program. So, duality theory, I'm sweeping a few details under the rug. If you want to see them, I'm happy to talk about them later. But we're going to use duality theory just like we did it before. And we're going to, before we were able to come up with a strategy for Alice to cheat, now we're going to come up with a new banker. Okay? So, strong duality, duality theory, it's all magic. Now we're replacing this banker with this banker. Okay? And now we're going to see what this banker does. She's going to create some GPT state. She's not going to choose it probabilistically, she just chooses some subnormalized GPT state. There's some subnormalization going on. She sends it out into the wild, counterfeiting machine, sends it back, and what does she do? Well, she has a very interesting verification. She just basically throws it all in the garbage and just accepts. Okay? She has a trivial verification where she just throws everything in the garbage and says, yep, I accept it. Okay? Seems silly, but it's good for bounding. For one thing, you can't cheat this banker. You don't need an elaborate strategy to clone all this money and send it back to her because she's not even going to verify. She's just going to accept anyway. So you cannot cheat her. Okay, so the probability of when you have n copies is just going to decrease exponentially in n. Okay? And the way we've designed this banker is such that she's an upper bound on how much the original banker can cheat. So if the original banker could cheat with 70%, maybe she's 80%. But if the original one was strictly less than 1, so is this one. Okay? So that's the neat thing. Okay? And now, if you use basically a perfect parallel repetition theorem for cone programming, you can show that you can't cheat this banker either. That's the algebraic proof. Okay? Yeah, and that's the end of the proof. Okay, so some future work I want to look at. So coin flipping. So there's lots of other cryptography things that we could try to analyze. So coin flipping is one. Oblivious transfer. Oblivious transfer is a favorite of cryptographers. So it'd be nice to show that oblivious transfer is also impossible. Okay, even with GPTs, it's impossible with quantum. Yeah, and there's some kind of advanced stuff. There's GPT fully homomorphic encryption. So the quantum stuff is still being ironed out now. So it'd be nice to have a GPT version of that. And classical GPT-resistant cryptography. Okay, this is a big area now where people are taking problems that are hard for quantum computers. They're classical problems, but so far no one's been able to break them. Okay, and this is promising whenever we do build these near-term quantum computers or ones that are useful, they'll still be resistant. So bank information will still be protected. Okay, so this is getting very interesting because now you're getting into like the Church-Turing thesis. So now if you want to do things that are computationally efficient, these things are assumed to be physical. And there's all these theses out there that say everything you can do physically, you can also do on a Turing machine, classical Turing machine. So now if you want to start talking about solving NP-complete problems, now you get into some very interesting territory. Not that I know of, definitely. Well, cryptography is not based on NP-hard problems. It's mm-hmm. Yeah, there's. I think there's some circuit models where you can. Right. Yeah, I think some of the circuit complexity stuff you can get from BQP, and with GPTs I think you can get upwards of like sharp P or something like that. No, the particular sharp P complete I don't know the exact problem, but they've been able to find a GPT that satisfies it. That was work in Oxford. This was in the last few years. So I think a couple years ago they found the sharp P complete upper bound, or sharp P upper bound, and then recently, last year or two, maybe a year after, is by Neil DeBodra and some co-authors. Yeah. So there are some limits. You can't just do absolutely anything you want. But yeah, that's a very good point. Okay, so quick summary. GPTs are interesting. I hope I conveyed that to you. If you already knew GPTs, hopefully you still feel this way. Coding programs are very useful. As far as I know, they haven't been used very much. As far as I know, these are the first applications of it in GPTs, and there's only a handful in quantum. Okay? So even if you found a code programming that's useful in quantum, I think that would be very interesting as well. It's only a few papers. Bitcoin is still impossible. Unforgeable money is still possible, and there's lots more to do. Great. Thank you very much.